were considering what is P, what is NP. NP is the class of languages accepted by non-deterministic Turing machine in polynomial time. P is the class of languages accepted by deterministic Turing machine in polynomial time. Is NP is equal to P is still an open problem. Just recall the connection between problems and languages. For example, does M accept W is the problem, and the corresponding language is denoted by strings having the form MW is the corresponding language. So, every problem we can have a language representation. So, is CFG ambiguous? Given a CFG ambiguous, the language will be encoding of G, which is an encoding of G which are ambiguous. A language corresponding to that will be L. It will accept all grammars which are ambiguous. G is ambiguous. So, you can talk about problems, usually we use the symbol pi and the corresponding language is L. So, you talk about pi in NP, pi in P or L in NP, both are equivalent. Now, when you look at a language representation for a problem, certain things you have to consider. For example, if you have a Boolean expression, is the Boolean expression satisfiable? Then for example, x1 plus x2 not x1 plus not x2 or something like that, this is a Boolean expression. Now, how do you represent, this is a string, you can represent it as a string, but you must x1 x2 instead of writing x1 x2 you can use numbers for the variables. Okay. So, for example, there are two variables. Okay, so 0 and 1 or you can use binary representation or just decimal representation 1 and 2 you can use. So, this one you can write as 1 plus 2 not 1 plus not 2, something like that you can use. Each variable is represented as a decimal number. If there are n variables up to n decimal numbers you will use. So, there are things which you have to be careful. Numbers we can represent as decimal or binary, does not matter, or any other base, because from one base you can the length will be only increased by a constant. Okay. Log n to the base a is equal to log n to the base b log b to the base a, right. So, this is a constant. So, from one base to another the length will be affected only by a constant factor, but if you use unary representation 2 power n will use 2 power n bits. In binary, this is in unary, in binary it will use n plus 1, drastically change. So, you should not consider unary representation, any other representation is okay, because you have to scan the whole input. If you are going to represent it in unary, time will be exponential, increase exponential, right. So, proper representation you have to choose. You can have graphs, given a graph something like this with nodes 1, 2, 3, 4. The question is, does it have a click of size 3? Click is complete subgraph. Does this graph have a complete subgraph of size 3? It has, a triangle is there. But how do you represent this graph? There are 4 nodes and some edges. You choose some proper representation like 1, 2, the edges you represent 1, 3, 2, 3, all edges starting from 1 first and all edges starting from 2, then all edges starting from 3, 4. You can represent it as a string like this. So, any problem you can represent in a proper manner as a language. Now, does it have a size of click of size 3? The 3 you can put in front. So, any problem proper way you can consider a language. So, you can talk about a problem being in NP, a language being in NP without any difficulty. Now, let us see what is polynomial time reducibility. We say that L dash is polynomial time reducible to L if there is a polynomial time bounded Turing machine that for each input x produces an output y that is in L if and only if x is in L dash. So, from one language it is transforming into another language, okay. That is, and the transformation is done by a deterministic Turing machine in polynomial time. This is called polynomial time reducibility. I will read again. We say that a language L is polynomial time reducible to L dash is polynomial time reducible to L if there is a polynomial time bounded Turing machine that for each input x produces an output y that is in L if and only if x is in L dash. If L dash is polynomial time reducible to L, then if L dash is in NP, then L dash will be in NP if L is in NP, and if L dash is in P, L dash is in P if L is in NP. If one L dash is polynomial time reducible to L, and if L is in NP, L dash will be in NP. If L is in P, L dash will be in P. A slightly the same definition putting in a slightly different manner. Same definition only is stated in a slightly different way, that is all. A polynomial transformation from a language L1 contained in sigma star to a language L2 contained in sigma 2 star is a function f which transforms strings in sigma 1 star to strings in sigma 2 star that satisfies the following two conditions. 1, there is a polynomial time deterministic Turing machine that computes the function f, that is it transforms L1 into L2. For all x in sigma 1 star, x belongs to L1 if and only if f of x belongs to L2. Then you use the symbol L1 is reducible to L2, L1, L2. The symbol is used. Now, having defined this, let us see some more things. If L1 is polynomial time reducible to L2, then if L2 is in P, then L1 will be in P, because L1 polynomially you can transform to L2 and you can accept L2 in polynomial time. If L2 is in P, that means L2 can be accepted in polynomial deterministic Turing machine, can accept it in polynomial time. L1 can be accepted by a deterministic Turing machine in polynomial time, because from L1 you can convert it to L2 and then accept L2 in polynomial time. This is also a polynomial and acceptance of L2 is also polynomial. So, L1 can be accepted by a deterministic Turing machine in polynomial time. Okay. Now, transitivity you can very easily see. if L1 can be polynomially transformed to L2 and L2 can be polynomially transformed to L3, then obviously combining the two, one Turing machine can transform L1 to L2, and that is a deterministic Turing machine working in polynomial time, and another Turing machine can transform L2 to L3, that is also done by a deterministic Turing machine in polynomial time. So, combining the two, you can have a Turing machine which transforms L1 to L3 in polynomial time. So, if L1 is polynomial time reducible to L2 and L2 is polynomial time reducible to L3, then L1 is polynomial time reducible to L3. And when do you say L1 and L2 are polynomially equivalent? If you can reduce L1 in polynomial time to L2 and you can also reduce L2 in polynomial time to L1. Okay. There is something else called log space reducibility. I will not consider it now. So, all these reductions which we are going to consider are polynomial time reductions, right. So, with this we will proceed further. In a way, what is a complete problem? You have a class, in that class you pick up some problems and show that they are as difficult as any other problem in that class. Those problems are called complete problems. This need not be NP, we are going to study about NP, but NP complete problems, but it can be other class also. Any class you take, you find out some problems, and these problems you show that they are as difficult as any other problem in that class. Okay. So, those problems are known as complete problems for that class. You also have piece space complete problems and so on. Okay. Let C be a class of languages. This is a general definition, then we will define for NP. What is an NP complete problem? Let C be a class of languages. We say a language L is complete for C with respect to polynomial time reductions if L is in C and every language in C is polynomial time reducible to L. There are two conditions to be satisfied. Generally we take polynomial time reduction, sometimes certain cases you have to take log space reductions and so on. So, that is for some other class. Here generally we are taking polynomial time reductions. So, I will repeat this definition again. Let C be a class of languages, this is a class say, and the language L is said to be complete for that class. It is as difficult as any other problem in the class. A language L is complete for C with respect to polynomial time reductions if L is in C and every language is C is polynomial time reducible to L. Two conditions have to be satisfied. Now, let us go to the definition of NP completeness, same thing, but we will specify NP specifically. A language L is defined to be NP complete if L belongs to NP and for all other languages L dash belonging to NP, L dash is polynomial time reducible to L. So, now we are restricting to one class, the class NP. A language, I will repeat again because these definitions are important. A language L is defined to be NP complete if L belongs to NP and for any other language L dash belongs to NP, L dash is polynomial time reducible to L, right. Now, what is NP hard? There are two conditions, one is this, right, the second is this. any other language, L dash is polynomial time reducible to L. There are two conditions, right. If the first condition is not there, but only the second condition is there, the language is said to be NP hard, right. This language means you can also talk for problems. When you talk about languages, corresponding problems also you can talk, right. Lemma, if L1 and L2 belong to NP and L1 is NP complete and L1 can be polynomially reduced to L2, then L2 is NP complete. So, suppose this is the class, you are considering the class NP and this is the class. L1 and L2 are in this, L1 is L1 is NP complete, and if you can reduce L2 to L1, then L2, I am sorry, if you can reduce L1 to L2, then L2 is also NP complete. How do you prove this? Now, I know that L1 is NP complete, L1 is NP complete. Okay. I want to prove L2 is NP complete. Right. Now, there are two conditions which have to be satisfied. What are the two conditions? You have to show that L2 belongs to NP, first condition, but that is given, L1 and L2 are in NP, so this is satisfied. The second condition, any L dash belonging to NP, for any L dash belonging to NP, L dash is polynomially transformable to L2. This is what we have to prove. But L1 is an NP complete. We already know L1 is NP complete. So, L dash, if you take, it is polynomially transformable to L1, and it is given that L1 is polynomially transformable to L2, right. So, by transitivity you get this. So, the second condition is also satisfied. Okay. So, that is this lemma. So, now what you have to do is, you are given a language L or a problem pi, new problem pi, then you want to show it is NP complete. How do you show that? First of all, you show L is in NP, or corresponding problem you talk about, pi is in NP. There is some known NP complete language L dash such that L dash can be reduced to L in polynomial time. You can talk about in the as problem, a problem pi is said to be NP complete if pi is in NP and there is some known NP complete problem pi dash such that pi dash is polynomial time reducible to pi, okay. Right. Okay. So, the class is like this, NP is this class, and P is like this, NP complete problems, current thing looks like this. Whether this is proper inclusion or not, we do not know, it is still an open problem. So, these problems are such that even for one problem, if you give a polynomial time algorithm, deterministic polynomial time algorithm, everything collapses, right, P becomes equal to NP. Even if you are able to give a solution deterministic polynomial time algorithm for one of this, then NP becomes equal to P, right. Okay. Now, if you know one problem to be NP complete, other problems you can show to be NP complete by some other problem, by reducing this to this. If you know one problem to be NP complete, you can reduce polynomial time reduce to another new problem, and new problem is NP complete. Then once you know this, you can reduce it to L2, you can reduce it to L3 and so on, right. But first one problem you have to show to be NP complete, that is the Boolean satisfiability problem. So, we will show that Boolean satisfiability is NP complete, or this is what we want to show. The problem of determining whether a Boolean expression is satisfiable is NP complete. Okay, this is known as Cook's theorem. So, we will consider the proof for this now. So, we will consider how to prove that. Now, in order to show that Boolean satisfiability is NP complete, first of all let us consider the representation of it. How do you represent a Boolean expression? As I told you, you can use something like say x1 plus x2 plus not x3 to x4 plus not x5, something like that, as 1 plus 2 plus not 3, 4 plus not 5. The symbols you use are left parenthesis plus right parenthesis. You may also use star, here star is omitted, for AND you use star, for OR you use plus, and then the not symbol, and the variables are represented by decimal numbers. Now, if you have n variables, to represent each one of them in decimal or something like that, you require something like C log n bits, right. But let us not bother about this factor, because ultimately when you have a polynomial time, multiplying by a log n is not going to affect the polynomial or the non-polynomial time of it. So, let us not worry about that. Assume that every variable is represented as one symbol like this. Now, there are two aspects to proving something is NP complete. You have to prove that L is in NP, and 2, any language L dash in NP is, you can transform to L, is not it. Now, how do you show that? First, this is in NP. Can you have a non-deterministic Turing machine which will take a Boolean expression as input and say whether it is satisfiable or not in polynomial time? You can have a non-deterministic Turing machine which will take as input the given Boolean expression, it will non-deterministically guess an assignment. If there are n variables, there are 2 power n possible assignments. If you use a deterministic Turing machine, one by one you have to try the 2 power n assignments. But if you use a non-deterministic Turing machine, non-deterministically you can guess a value for each of the variables. That is, you can non-deterministically guess an assignment. After guessing that assignment, you have to evaluate that expression. How much time it will take to evaluate that expression? Can it be done in polynomial time? It can be done in polynomial time, because it depends on the parsing algorithm you have. For a context free grammar can generate all Boolean expressions and how much time that parsing algorithm will have and so on. Or otherwise, even look at it as the given string is of length n, the Boolean expression, we are considering in terms of the input, is not it? Input is of length n. At the most you can have n sort of order n parenthesis, nested parenthesis you can have. So, make one pass evaluate, all the innermost things will be evaluated, make another pass you evaluate and so on. In one pass will take order n time. At the most you have to make n passes. So, in order n squared time anyway you will be able to evaluate. Once you are able to guess an assignment, evaluation of the expression will take order n squared time. Some shifting this way, that way, all those things will be there, that does not matter. Our aim is whether it is a polynomial or not. The constants do not matter so much at this stage, right. So, in order n squared time you can have a non-deterministic Turing machine which will evaluate the Boolean expression and say whether it is satisfiable. If it reduces to 1, it is satisfiable. If it does not reduce to, if it reduces to 0, right. So, L is in NP, this is very clear. The second is any Turing machine, any non-deterministic, any language L dash accepted by a non-deterministic Turing machine is polynomially transformable to L. This is the proof. What we do is consider a non-deterministic Turing machine working in polynomial time. So, there is a Turing machine M for which the time complexity is a polynomial P n. Okay. Now, given M and input W, M is a non-deterministic Turing machine which will accept W in polynomial time, accept or not. Okay. So, given M and W, you construct a Boolean expression W naught. This is a Boolean expression. Which will be satisfied, this W naught will be satisfied if and only if M accepts W. Okay. Given M and W, you write an expression W naught, a Boolean expression W naught, such that W naught is satisfiable if and only if M accepts W. Given M and W, write W naught, form an expression W naught such that W naught is satisfiable if and only if M accepts. But the point is, given m and w, to construct w naught it takes only polynomial amount of time. There is a deterministic polynomial time algorithm which will construct w naught given m and w. Okay. So, there w naught can be, this is the main point, w naught can be constructed in deterministic polynomial time from m and w. So, if you do that, what we are showing is any L dash in NP, this is some language non-deterministic Turing, you can convert to this Boolean satisfiability if I put it as L naught in polynomial time, right. So, if you prove this, that means we are showing that Boolean satisfiability is NP complete. Now, in our, how do we go about constructing W naught from M and W? There are some assumptions we have to make. Assumptions maybe I will write here itself. M has states Q1, Q2, Qs. This is the set of states as state set. This is the set of states and this is the initial state and this is the final state. Without loss of generality you can assume that. Then the alphabet gamma is x1, x2, xm, m symbols are there in the tape alphabet and the first symbol you can take as the blank symbol. One of them you have to take as blank, does not matter which one. Okay. So, the initial ID of the Turing machine is say some q naught, then the next ID will be q1, next ID will be q2 and so on. After some steps at QQ it will accept or reject, right. Now, what is this Q? Q is less than or equal to P of n. Maximum number of steps will be P of n. Within that step it will accept, right. So, Q is less than or equal to P of n. Okay. These are some assumptions we make. One or two more things also we have to take into account, that I will mention. Now, in order to find the expression W naught, we have to use some Boolean variables. What are those variables? You have a set of variables of the form CIT, a collection of variables of the form CIT, and what is the meaning of this variables is CIT is equal to 1 if the ith cell in the tape contains the jth symbol, at time t. The tape will be like this. The input is of length n, initially it start, you will be starting at this point initially. Initial state will be q1. If the ith cell contains the jth symbol at time t, then Cij will be equal to 1, otherwise 0, otherwise 0. Now, what is the maximum number of cells you will require? See, machine starts here and it has to halt within Pn steps. So, at the most it will need up to Pn cells, even if it moves just forward, it will be going up to the Pnth cell. So, what is the range for I? 1 to Pn. From the first cell it can go up to the Pnth cell. It will not use more than that because the time complexity is P of n. What is the range for j? J can be any one of the m symbols, x1, x2, xm we have defined. So, it can be any one of the m symbols. So, the range for j will be 1 to m. What is the range for t? Initial ID is time t is equal to 0, right. Initially you start at time t is equal to 0 and you can go up to time Pn. There is a small thing we have to note here. From ID Q0, you go to Q1, you go to Q2, and after some step it stops. That Q will be less than or equal to Pn. If it is less than Pn, we want all the IDs to go up to Pn steps. We do not want to distinguish between something which is less than Pn and equal to Pn. So, the other IDs here, all these are taken identical to Qq. Next step also it is remaining the same, no move. So, that we assume that everything takes Pn steps. So, how many such variables will be there? I ranges from 1 to Pn, t ranges from 0 to Pn, j ranges from 1 to m is a constant. M is a constant, S is a constant. Number of states is Q1, Q2, Qs, S is a constant. So, you have order p squared n variables of this form, right. This is one set. Another set of variables HIT. HIT is equal to 1 if the head is scanning the ith cell at time t. You have variables, these have meaning like this. HIT is equal to 1 if the head is scanning the ith cell at time t, right. So, what is the range for I? 1 to Pn, range for t 0 to Pn, again order p squared n. Variables will be there. Third set of variables S kt, state S denoting the state. This is equal to 1 if the state is qk at time t. Now, k of course will vary from 1 to s, range for k is 1 to s, For t it is 0 to Pn. So, here you have order P of n variables. Okay. Now, each of these variables we assume that when you write the expression it takes only one unit or one symbol, it is represented as one symbol. Actually, since there are order p squared n variables, you have to represent them means some, each one you have to represent by a in a binary notation or something like that. So, another log n factor will be there. So, we are not worried about that log n factor, because ultimately it will not affect the polynomial or not the polynomial aspect of it. So, each variable is taken as one symbol for our calculation at present. Now, this expression W naught you have to write, given m and w you have to represent W naught, and W naught is satisfiable if and only if it represents a sequence of moves, like which leads to acceptance q naught, q1 etc. up to qq, qp. W naught is, you have to write W naught in such a way that it will become satisfiable if and only if there is a valid sequence of IDs, okay, leading to acceptance. So, what are the conditions? You have to look into that. These are the conditions you have to consider. The head is scanning only one cell at any instant. Head will be scanning only one cell, and each cell contains only one symbol at any instance. State is unique for a particular t, time instant t you will put for a particular t. There can be only one state at any instance, the machine can be in only one state. The contents of the cell pointed by the head alone changes in the next instant. The change is specified by a move of the Turing machine. 6, you have to take care of the initial ID and you have to take care of the final ID. Now, we are assuming that each variable is represented by a symbol. It's this assumption we are making, otherwise you have to multiply by a log n factor, that is what I said. Now, let us consider, for simplification we will use one more notation. An expression using R Boolean variables u x1 x2 xr, this is defined like this, it is x1 plus x2 plus xr and product of factors of the form xi plus not xj I not equal to j. This is a u x1 x2 xn is a Boolean expression which is of the form x1 x2 xr into product of factors of the form not xi plus not xj, where I is not equal to j. You have all of them. So, for example, u x1 x2 x3 will be x1 plus x2 plus x3 not x1 plus not x2 not x1 plus not x3 not x2 plus not x3, right. It will be like that. For R you can write like that. Now, when will this take the value 1 or true? When exactly one of them is 1 and all the others are 0. When exactly one of them is 1, it will take the value 1. If none of them are 1, it will take the value 0. If two of them are 1 also, it will take the value 0. Why? If none of them is 1, all are 0 means this factor will be 0. So, the total expression will be 0. If two of them are 1s, then there will be one factor. If ij are 1, there will be one factor not xi plus not xj, that will take the value 0. So, the expression will be 0. So, this is equal to 1 if and only if exactly one of x1 x2 xr is equal to 1, others equal to 0. Now, what can you say about the length of this expression? There are R variables. What can you say about the length of this expression? This will be R. How many factors will be there? For 1, if you take x1, there will be a factor with x2, x3, xr, r minus 1 factors. Then if you take x2, there will be factors with x3, x4, etc. So, that is r minus 2 and so on up to 1. How many factors like that it will be there? 1 to r minus 1, that is r into r minus 1 by 2 factors. Each factor, how many symbols it will take? 1, 2, 3, 4, 5, 6, 7, some constant number, right. And so, it will be something like r into r minus 1 by 2 into some constant k, plus this one is r into r, then some other constant L. So, anyway the length will be order r square. The length is order r square. This is important. So, we will make use of this notation for writing the expressions for those conditions. So, there are 7 conditions which we have specified. One by one we will write the expressions for them. So, what is the first condition? The first condition is the head is scanning only one cell at a time. So, AT is this expression, at time t the head is scanning only one cell. So, this can be the condition, you can write like this: u of h1t, h2t, h pn. What does that mean? The u is this expression, right. So, head will be scanning only one cell at a time. So, only one of the variables has to be 1, rest of them have to be 0, then only this will become 1, right. So, the whole expression is, this should hold for instance t is equal to 0, 1, 2 up to Pn. So, the expression A which satisfies the first condition is A0, A1, A2 up to A Pn. Now, what can you say about the length of A? Each AT is order p squared n. Here if it is r, it is r squared, here it is Pn. So, it is order p squared n and you have Pn of them. So, the length will be, length of such an expression will be order p cubed. Okay. The second condition is each cell contains only one symbol at a time. So, you write it as pi bi. The expression for that will be bit is at time t only one symbol will be there, that is this is u of ci1t or ci2t cim. The ith cell can contain the first symbol or the second symbol or the nth symbol, where the product is over int. Right. Each cell can contain only one symbol at a time. So, at time instance t the ith cell can contain only symbol 1 or symbol 2 or symbol m. So, this expression is equal to 1 only one of them is 1 and the others are 0, is not it, the way you have written u. So, this expression makes sure that at any instance each cell contains only one symbol, right. And what can you say about the length of B? B is this expression. This is the product over int, where I will range from 1 to Pn, t will range from 0 to Pn. Okay. The length of this will be order m squared, because you have m variables here. So, the total, this is a constant, m square is a constant, this is a constant, but this I ranges from 1 to Pn, t ranges from 0 to Pn. So, the whole length will be order p squared. Then the third condition, what is the third condition? The state is unique at any instance. Okay. So, S1t, S2t or S, totally there are S states, St. Only one of them I can put St is equal to this, u of this, and expression C is S0, S1 up to S. That means only one of them will be 1, others will be 0 for a particular t, and you have to consider t varying from 0 to Pn. The length of this is order s squared, but s is a constant, right. So, the length of this is a constant, but this varies over from 0 to Pn. So, the total length of this expression will be order p of n. Then fourth condition is only the cell scanned by the head will change, the contents of the cell scanned by the head will change, the rest of them will remain as they are, isn't it? If the head is scanning this one, it will change this symbol, but rest of the portion it will be the same. So, that is C I j t is the same as C I j t plus 1, or either the head is scanning the ith cell. If head is not scanning the ith cell, the contents of the cell I is the same at time t and the time t plus 1, right. This is the expression, but you have to take the product over I j t. Right. Again j will be 1 to m, I will vary from 0 to 1 to Pn, t from 0 to Pn. This expression will also be of length p squared. The fifth condition is, the next move is specified, this is the expression d. The expression E satisfies the fifth condition. What is the fifth condition? The next move is specified by the moves of the Turing machine. So, either the head is not scanning the ith cell at time t, or the state is not k at time t, or the ith cell is not containing the jth symbol at time t. Now, I want to specify the move for the case when the state is k and the ith cell head is scanning the ith cell and the contents is xj. So, if one of this is violated, it is okay, But if the head is scanning the ith cell, the state is k and the ith cell contains jth symbol, what will be the next situation? Next situation will be state will be some KL t plus 1, state will change to some other state, right, that is represented by KL, and head C ith cell will contain some other symbol at time t plus 1. Right, and the head will go to I minus 1 or I plus 1, isn't it. So, H I L t plus 1, this will be I minus 1 if the move is left, it is I plus 1 if the move is right. Actually, it is a non-deterministic theorem. So, what we are considering is a non-deterministic theorem. So, next move is not unique. There will be some possible choices. One choice is KL, JL, IL, there may be another choices. So, consider all possible choices, write them down. Okay. So, that is why you are using sigma here, not pi, sigma, this or this or this, one of the moves it will select. So, if the head is scanning the ith cell and the ith cell contains the symbol j and the state is k, the next move will be given by one of them. There will be L possible choices, each one you write. Otherwise, if it is not followed means head is not scanning the ith cell or the state is not k or the ith cell does not contain the jth symbol. So, this expression tells you about the next move of the, from one ID how do you go to the next ID, that is specified by this expression that is given by, actually this is E I J K T is equal to this, and you take the product E is I comma j comma, again j will vary from 1 to m, k will vary from 1 to s, I ranges from 1 to pn, t from 0 to pn. So, the length of the expression will be order p squared m. The sixth condition is initial ID. What is the initial ID? H10 at time 0, the first symbol will be spanned, state is 1, S10, and first C10, C20, CN0, this will get the input. Input is A1, A2, depending upon that you give the value here. Whichever symbol is there in the input you give. Then what can you say about C? N plus 1, 0, C n plus 2, 0 up to C Pn 0. Initially, you have the input in the first n cells and the rest cells are blank, and blank is x1 we have taken. So, this will be 1. As a notation we have taken the blank to be 1, x1. Then the final ID is just the state becomes 2 at time. Q1 is taken as the initial state, Q2 is taken as the final state. So, the seventh condition is given by this expression. These are all fixed length. This is of length n, this is only 1. am sorry, this is of length Pn. Pn. So, totally you have an expression, Boolean expression W naught, which is equal to A, B, C, D, E. If I denote this 6th condition by F and the 7th condition by G, the expression is A, B, C, D, E, F, G. So, what we have done is we have written expressions A, B, C, D, E, F, G for satisfying the 7 conditions, and we consider W naught to be equal to A, B, C, D, E, F, G. Right. What can you say about the length of A? It is order p cubed n, B, C, D, E they are p squared n, I am sorry, C is p n, B is p squared n, D is p squared n, E is p squared n, F is p n, G is 1. So, the total length of this is order, at the most it is order p cubed, that is a polynomial, right. Here we are assuming that one variable is represented as one symbol. You may have to use some representation for representing the variables, in which case there will be one more log factor, right. If suppose you are having n variables, you require log n bits to represent them. So, here the number of variables is order p squared n, log to that will be required. That does not matter, anyway one more polynomial factor will be, one more expression will be there. So, given m and w, you can write w naught, and the length of w naught is polynomial in n is the length of w, right. And since the length of w naught is like that, and there is, you know how to write this w naught. So, there is a systematic way of writing it. So, w naught can be written down from m and w in polynomial time. Its length is polynomial, and it can also be written down in polynomial time. Okay. So, any non-deterministic Turing machine M, if you take any non-deterministic Turing machine M, you take, and the input is w. From this you can write w naught in polynomial amount of, in polynomial time, right, deterministic polynomial time. That is, if L belongs to NP, then it is accepted by, L is accepted by non-deterministic Turing machine M, right. And you know that from this you can write down w naught such that w naught is satisfiable if and only if M accepts w. That is, L is polynomial time reducible to L naught. L naught is the Boolean satisfiability problem. This is Boolean satisfiability. Any language L in NP can be transformed in polynomial time to L naught. Okay. So, this shows that Boolean satisfiability is NP complete. So, we will continue in the next class. That is tomorrow 11 o'clock. Okay.